Hello, my name is Nurul Rahimah binti Muhammad Azmi with metric number B011910083. My responsibility is as a video editor and voiceover for introduction.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Syamimi binti Zulkifli. My metric number is B0119100015 and my task in this assignment is I'm going to explain the concept of the boundary condition and I will explain the idea with the related equation and derivation. Thank you and keep watching.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Khairunisa binti Khairuddin. Metric number B011910023 and I am responsible in providing a question and a step-by-step solution related to this topic, which is boundary condition.
Definition of boundary is a surface on which secondary electromagnetic sources are induced by the primary field so that the field beyond the surface vanishes. While boundary surface is different from an interface of two media because the field beyond the interface are not necessarily zero. There are three basic properties of boundary condition. First, perfect electric conductor (PEC). Second, perfect magnetic conductor (PMC). And third, perfect electromagnetic conductor (PEMC). Engineering view aspect of boundary condition is in analytic and synthetic.
Two different media such as dielectric and dielectric, conductor and dielectric, and conductor and free space. To determine the boundary conditions, we need to use the Maxwell equations. Then, we decompose the electric field intensity E into two orthogonal components, which is tangential component of E and normal component of E. Similarly, electric flux density D also divided into tangential and normal components as well. Dielectric boundary conditions. Figure 1 shows an interface between medium 1 with permittivity epsilon 1 and medium 2 with permittivity epsilon 2. In the general case, the interface may contain a surface charge density rho s, then E1 and E2 can be decomposed into components tangential and normal to the boundary. To derive the boundary conditions for the tangential components of E and D, we consider the closed rectangular loop ABCDA as shown in figure 1. Then we apply the conservative property of the electric field in the Maxwell equation, which states that the line integral of the electrostatic field around a closed path is always zero. This rectangular closed path, half of the path is in region 1 and half of the path is in region 2. Then we apply the E dot dl in this closed path, that we only take the magnitude parts of E1 and E2. Then we come up with this integration. So after cancelling some terms, we have E2t minus E1t delta L equal to 0. If we assume that the dimensions are very small, that delta H equal to 0, then delta L equal to 0 as well. From here, we have E1t equal to E2t. Thus, the tangential components of E are the same on the two sides of the boundary. In other words, if P cause no change on the boundary and it is said to be continuous across the boundary. Since we know that the electric flux density D equal to epsilon E, again D is written into tangential and normal component. Then we express in terms of electric field, then we get these two terms. After putting these two terms in equation 1, we get E1t over epsilon 1 equal to D2t over epsilon 2. Thus, tangential component of D undergoes some change across the interface. Hence, dt is discontinuous across the interface as it is depend on the value of epsilon 1 and epsilon 2. Then, we apply the second Maxwell equation, that is closed surface integral d dot ds equal to Kn closed. Here we take a closed cylinder. Half of the cylinder is in region 1 and half is in region 2. Now this closed cylinder has a surface charge density rho s and its cross-sectional area is delta s. Then we apply the closed surface integration that was divided into three surfaces, top, bottom, and side. Here the surface integration of the side is 0, that is cancelled due to symmetry to the boundary. The bottom surface having direction opposite to the normal component. So after taking these two terms, surface integration of top and bottom, we have the equation 3 and 4. Note that if there is no free charge at the interface, that is rho s equal to 0, thus the equation 3 becomes d1n equal to d2n, hence the normal component of d is continuous across the interface. From equation 4, since d equal to epsilon e, then we have epsilon 1 e1n equal to epsilon 2 e2n. Hence, the normal component of E is discontinuous across the interface. Application of boundary conditions. The boundary conditions can be used to determine the reflection of the electric field across the interface. The XY plane is a charge-free boundary separating two dielectric media with permittivity epsilon 1 and epsilon 2 as shown in figure 2. If E1 and E2 are given by these two terms respectively, the X and Y components of the field are tangential to the boundary and the Z components are normal to the boundary. At a charge-free interface, the tangential components of E and the normal components of D are continuous. Consequently, then we have these terms. Therefore, we can rewrite the equation for E2 as below. Then, the tangential components E1t and E2t can be found by using these two formulas respectively. Then, the angle of theta 1 and theta 2 are then given by these two formulas respectively as well. And the two angles are related by tangent theta 2 over tangent theta 1 equal to epsilon 2 over epsilon 1. Conductor dielectric boundary conditions. Consider the case where medium 1 is a dielectric and medium 2 is a perfect conductor. In a perfect conductor, there is no electric field and no electric flux density. Therefore, E2 equal to D2 equal to 0. Then from equation 1 earlier, we have E1t equal to E2t equal to 0 and D1t equal to D2t equal to 0 as well. Hence, for the normal components for conductor is also 0. And from equation 3 and 4 earlier, the normal components for dielectric are given by this following equation. Conductor free space boundary conditions. For free space, we know that epsilon r equal to 1. Then we can write the equations for tangential and normal components of electric flux density as the following. Hence, the electric field E must be external to the conductor and normal to its surface.
Example and step-by-step solutions. The figure below shows three planar dielectric slabs of equal thickness with different dielectric constant. If E not in air makes an angle of 45 degrees with respect to Z-axis, find the angle of E in each of the other layers. From the given picture, dielectric constant for layer 1 equal to 3 epsilon naught, for layer 2 equal to 5 epsilon naught, and for layer 3 equal to 7 epsilon naught. We need to know the related equation to solve this type of question. So the equation is tangent theta 2 divided by tangent theta 1 equal to epsilon 2 over epsilon 1. We have all the information that we need to calculate for angle theta. To calculate theta 1, we know theta 0 equal to 45 degree and dielectric constant equal to epsilon naught. While for dielectric constant for medium 1 equal to 3 epsilon naught. So we solve the equation to get the answer for angle theta 1. To calculate for theta 2, we have to use the angle of theta 1 that we got, which is 71.56 degree and the electric constant of 5 epsilon naught. We solve the equation and we got 78.69 degree for theta 2. We repeat the same step to find theta 3, then we solve the equation and then we get the answer for theta 3. Therefore, angle theta 1 equal to 71.6 degree, angle theta 2 equal to 78.7 degree, and angle theta 3 equal to 81.9 degree.